this part on the outside is a union of round disks. And I'm enumerating the round disks here to try to figure out the limit set. The limit set is this very furry tree-like structure that's left over. And this is one instance, so a borderline instance of the Alfors conjecture where, in fact, the limit set by a result of Bishop and Jones is known to have Hausdorff dimension 2, but it really should have measure 0, despite the fact that it looks like it has interior in this picture. If we waited millions of years, these circles would eventually creep in, and we just get an extremely furry object here. So that's a terrific result that was originally formulated by an analyst. And it brings to mind the following comment of Hardy. Hardy writes, "The mathematician's subject is the most curious of all. There is none in which truth plays such odd pranks." And one of the odd pranks is that there's a tremendous amount of geometric topology and complex three-dimensional arguments that are used to resolve what I'm sure Alfors conceived of as an analytic question, having to do with maybe the behavior of harmonic functions on the quotient 3 manifold, or maybe directly having to do with something with Green's functions in the plane. So it's really an odd prank that there's so much topology, and really quite deep topology, that was used to finally resolve this allegedly analytic problem. And as Peter mentioned, let's see if I can get this. There's also a recent result by Douadi, Bouffe, and Sherry Todd about the existence of a Julia set of positive measure in the quadratic family. So this is, both of these sets are very difficult to draw. This is a picture due to Sherry Todd. This set is an approximation to a Julia set where the black part has positive measure. And Sullivan made a very productive dictionary between these two subjects, which I've personally tried to contribute many entries to. And it's perhaps at first blush a bit of a surprise that in one language we have one statement, and the other language we have the contrary statement. But this is not correct. So in fact, what all of these people here proved altogether, and I should add here Minsky and Brock, if I want to include in addition, the ending lamination conjecture. They proved a much deeper theorem which gives a precise topological description of every possible hyperbolic 3-manifold, and even a description of this manifold up to quasi-isometry. And we're still shooting for the same kind of thing in complex dynamics, and the problem is still open. And this problem, which I've described here, would have been solved if we had had a negative solution to this business. If all the quadratic Julia sets had measure 0, would have implied the following problem, which is still open, namely, if you take a quadratic polynomial and you start iterating the critical point, z equals 0, and this critical point remains bounded under iteration, well, how can that happen? And one possibility is there's an attracting cycle, and that this critical point is being pulled towards that cycle, and as a result, it has to remain bounded. And the conjecture, which is extremely elementary, I mean, this is the whole statement of the conjecture, is that that's the only way this can happen. I'm waiting for a correction from the audience. Actually, this conjecture is false, as stated, after changing C a little bit. So in terms of this picture that's often drawn of the Mandelbrot set, which represents the space of quadratic polynomials, we believe that this blue part consists exactly of the values of C where there's an attracting cycle. And by definition, the Mandelbrot set consists of exactly the C such that the orbit of C of 0 remains bounded. And so the belief is that the interior of this set, which is known to be dense, consists of the point where there's an attracting cycle. And I should mention that this conjecture, which was called, starting in 1985, MLC by Douadi and Hubbard. And it's open. And the other conjecture is popularly called ELC, the ending lamination conjecture. And this has been now completely settled partly with the work we celebrate at this meeting. Okay, so there's, on a deeper level, the proof that the boundary of the Mandelbrot set is locally connected, which is a stronger statement than this conjecture, remains open and potentially carries as much combinatorial and topological challenge as the ending lamination conjecture did. Okay, so as a student of Dennis Sullivan, I was very interested in this area involving dynamics and quasi-conformal maps and Teichmüller theory, but the remaining problems all seemed too hard. So I tried to find another collection of ideas, dynamical in nature, which would use complex analysis and renormalization and Teichmüller theory, but would be much more linear. And I want to describe some results in that direction today. So these will be results that concern the moduli space of Riemann surfaces of genus G. So this is a 3G minus G minus 3-dimensional complex manifold, at least when G is 2 or more. And it's known to be a complex orbifold, in fact, an algebraic variety. And it comes with a natural metric. So you should think of moduli space as having a shape. The metric I'm going to be concerned with is defined by the following property. If you have a holomorphic map from the hyperbolic plane into the moduli space, then this map should shrink the hyperbolic metric. It should be distance decreasing. And there's a unique metric which is as big as possible and still has that property, and this is called the Teichmüller metric or the Kobayashi metric. Now, the dynamics, I'm going to discuss some dynamics over moduli space, but moduli space is very different from for example, a hyperbolic manifold or a spherical space form in the sense that rather than being homogeneous, the way a space of constant curvature is, it is completely inhomogeneous in this metric. So if I brought in a copy of moduli space and sort of a piece fell off on the floor, you could pick it up and you would know exactly where it came from just by the shape of that piece. And that's made precise by a theorem of Royden, which says that if you know, in fact, the unit ball in the tangent space at this metric, well, this metric is not Riemannian. The unit balls turn out to be some complicated convex sets. If you just know those convex sets, you can recover the Riemann surface, which is represented by that point. OK, so it's totally inhomogeneous. And because it's so inhomogeneous, it appears to be a very static object. How could you possibly transport one point to another? However, it acquires a dynamical flavor if we pass to certain bundles. And the bundle I'm going to be interested in is the bundle of holomorphic 1 forms over moduli space. So let me just remind you that if you have a Riemann surface, say compact of genus G, then it has no non-constant holomorphic functions on it. But it wants to. I mean, this is what Riemann surfaces are for. So it has the next best thing, which is it has the derivative of holomorphic functions on it. That is, locally, there are 1 forms. There are 1 forms on this space, which are locally just the derivatives f prime of z dz of holomorphic functions. And to specify this holomorphic 1 form is the same thing as to specify f of z up to an additive constant. So when you give a holomorphic 1 form to a Riemann surface, what it does is it gives you near every point a chart that is a map of a neighborhood of that point into the complex plane by f. And as long as you're away from the zeros of the form, that map is a local diffeomorphism. And it's well defined up to this constant of integration, c. So to give a holomorphic 1 form is the same thing as to give a way to build your Riemann surfaces out of squares. Because you can take near the image of this point a square in the complex plane and pull it back, and you get what you could call a square on this surface. And then you have squares near other points. And when these 2 squares overlap, they differ only by a translation. So we get a canonical flat metric on the surface, actually with certain singularities at the zeros. But you should think of this as being a way to make the Riemann surface out of squares. OK, now the space of such 1 forms is a is a g-dimensional complex vector space. That's another definition of the genus of the surface. And what's remarkable is that when you take these one-forms and you put them all together to form a bundle over moduli space, where the fiber over a given surface is just the vector space of holomorphic one-forms on that surface, that this bundle has a dynamical nature. It admits an action of SL2R, the 2 by 2 matrices of determinant 1. So where does this action come from? Well, first, there's an obvious action of the circle on this space. If you take a one-form, you can just multiply it by a complex scalar of modulus 1. And it's another one-form on the same Riemann surface. So that gives you an action of S1. How does the diagonal group inside of SL2R act? It acts in the following way. You have a Riemann surface that's built out of squares. And now you take the squares and you stretch them to form rectangles. And the way you stretch them is dictated by a 2 by 2 real matrix. And what you do then is you take your Riemann surface and you change all of the squares simultaneously to rectangles. And the result is that you get a new Riemann surface, x sub a, whose charts are now locally given by a composed with f, and a new holomorphic one-form on that surface. And that gives you an action of SL2R on the bundle of holomorphic one-forms, on the space of holomorphic one-forms on a Riemann surface. Now, this action turns out to be intimately connected to the metric I just mentioned. So SL2R also acts transitively on the hyperbolic plane. And it turns out that if you take an SL2R orbit in this bundle of one-forms and project it down to moduli space, what you get is a map of the hyperbolic plane, here we go, into moduli space. It covers such a map. So the orbits of this group cover certain complex geodesics inside of moduli space, certain holomorphically immersed hyperbolic planes. And here's the question I want to address. What are the possibilities for the closure of a complex geodesic? Well, unfortunately, I only have an answer to this question in the case of genus 2. On the other hand, many of my colleagues are still working on surfaces of genus 1. So perhaps this represents progress. Anyway, genus 2 is the first interesting case. And the theorem here is that the closure of a complex geodesic is always an algebraic subvariety of moduli space. So let me make this concrete. Let's think about dimensions. The moduli space of Riemann surfaces of genus 2 is 3-dimensional. So the closure, if a subvariety, is either a curve, in which case, that's the first case here, it would then be an isometrically immersed algebraic curve, or it's the whole space. That's the last possibility. And that's by far the generic possibility. A typical complex geodesic will certainly be dense. And then it turns out there's an intermediate possibility, which is that the closure can be what's called a Hilbert modular surface. And these correspond to Riemann surfaces whose Jacobians have special symmetries, as we'll discuss shortly. So the general statement is simply that the closure is an algebraic variety. And there's every indication that such a result might hold in higher genus. But no one knows how to approach that at this point. However, I should give you some context for this result, which is that there's a beautiful theorem, one of the triumphs of the late 20th century mathematics, the proof of the Raghunathan conjectures by Marina Ratner. And a special case of that theory is the following. If you take an isometrically immersed hyperbolic plane inside of a hyperbolic n-manifold, and you take its closure, what you get is an immersed finite volume hyperbolic k-manifold. And that's quite amazing, because you see, if you take the closure of an individual geodesic inside of a hyperbolic manifold, it can be a terrific mess. It can be sort of a cobweb, locally cross-section, a Cantor set, or the Sierpinski curve, something completely wild, even from a topological point of view. But if you take the closure of a hyperbolic plane, a two-dimensional object, it's always geometric. And this theorem of Ratner's has several enhancements, and let me just mention that those enhancements hold in this case as well. Namely, not only can we say that every closure of an orbit of SL2R is some nice algebraic subvariety, but also the ergodic invariant measures for the action of SL2R come in a natural way from suitable measures on these algebraic subvarieties. So Ratner's theorem says that if you have a sufficiently rich group action on a homogeneous space, then the orbits and the ergodic invariant measures are all algebraic. They come from, so to speak, subvarieties. And this is a nonlinear or a non-homogeneous generalization of that kind of result. OK, so you might say then we've classified the SL2R orbits on the genus 2 moduli space, or over the genus 2 moduli space. Now, what does it mean to classify something? For example, if I prove that every 3-manifold can be triangulated, I now have a way to enumerate all 3 manifolds. I simply start triangulating them, throw out things that don't turn out to be manifolds, and then I have a list of all 3 manifolds. Now, have I classified all 3 manifolds when I've done that? Well, I would say not. I think to classify something, you have to do 2 things. You have to give explicitly all of the examples, and you have to tell me when you've given the same example twice. That is, you have to have some computable invariance to tell the different examples apart. And so I want to enhance this theorem by saying exactly what these orbit closures can possibly be. How can I classify them? Well, it turns out, the full space, that's pretty easy. And then these Hilbert modular surfaces turn out to be indexed by a single discriminant. They correspond to orders in real quadratic fields. So they are also well studied and classified, and this D turns out to be eminently computable. But what about these isometrically immersed algebraic curves? Where can we find those? Have they been previously studied in mathematics? Do they have names? So we can focus on that remaining problem in the following way. Suppose we have a 1 form, and its stabilizer inside of SL2R is a lattice. You see, for the orbit to be an algebraic curve, that means that the closure of the complex geodesic is an algebraic curve. That means the hyperbolic plane is being mapped into moduli space simply as the universal cover of some algebraic curve sitting in moduli space. And the stabilizer of this 1 form will simply be the fundamental group of that algebraic curve. So it will be a lattice in SL2R. So we can simply ask, for what 1 forms of genus 2 is the stabilizer of the 1 form a lattice? When are these sort of real affine symmetries of it a lattice in SL2R? Now, you might think, if you want to define these algebraic curves and find out what's known about them, that you should consult your local complex algebraic geometer or differential geometer or number theorist. But it turns out that that would be wrong. You should consult your local billiard theorist. So the people who have studied billiards in polygons are intensely interested in these curves and have done the most work on them so far. And why is that? Well, let me give you an example of a theorem about billiards. This is due to Veitch. So suppose you play billiards in a regular pentagon. So you consider trajectories which bounce off the sides in the usual mechanical way, equal angle of incidence and reflection. You'll notice that you see only 10 different slopes in this picture because the group generated by reflections in the sides is a finite dihedral group. But you see many parallel lines in each slope. And it doesn't look like any particular region of the pentagon is favored over any other region. What's being drawn here, I should say, is just one very long billiard path. And it seems to be going everywhere. So we can say that a billiard table is optimal, or it has optimal dynamics, if every trajectory is uniformly distributed. Now, that's too much to ask for, because you might have a trajectory that just comes back to where it started. And then, of course, it has no chance of going everywhere, because it's just periodic. So we say the dynamics is optimal if those are the only two possibilities. Either you see completely periodic behavior, the billiard trajectory comes back to where it started, or the billiard trajectory is uniformly distributed. It goes everywhere inside of the billiard table, and it spends an equal amount of time in each region of the table. OK, so just to illustrate that this is actually a condition on the billiard table, I want to show you an example of non-optimal dynamics. So suppose you practice bowling in your square basement, and you stand here and bounce the ball off the sides, and it comes back to where you started. You keep practicing like that. So there's a periodic trajectory in the square here, which is formed by the large table at the right-hand side of the screen. And then adjacent to this, we have a closet. And suppose we open this closet and allow the bowling ball to go roll around in there. Well, what happens is it rolls into the closet, it bounces around quite a bit, and then it comes back translated by some fairly random amount. So depending on the shape of the closet we've added, the trajectory of a randomly rolled billiard ball will fail to be periodic now at the angle of 45 degrees. I've drawn a very long trajectory here, and it shows no evidence of closing. On the other hand, it's still perfectly safe to store your valuable collectibles in the two corners of your basement, because the billiard ball is not interested in going there. It certainly is not dense. And so this is an example of a billiard table that has this intermediate behavior. It has geodesics that are neither periodic nor uniformly distributed. And much worse things can happen. But this is just to convince you that this intermediate behavior is certainly possible. And by the way, this is not just a pure theory. I mean, there are applications. This is a picture contributed by a billiard theorist named Moon Duchens from a billiard hall, I'm told, is in South Africa, and apparently has actual L-shaped tables. OK, so now how would you, as a mathematician, try to analyze billiards in an L-shaped table? Well, there's a simple idea which can also be used already in the case of a square rectangular table, and it's only slightly more complicated here. So what you do is you consider this red trajectory here, which is bouncing around in the upper right-hand table, and every time it hits a side of that table, instead of having it reflect, you just imagine the trajectory going straight through into a copy of the billiard table reflected through the side that the trajectory hit. So instead of thinking about the red trajectory bouncing, we think about it continuing in a straight line as this blue trajectory, but entering a new table. And then when it hits the side again, it enters yet another new table. And now when it hits the bottom side here, we could put yet another table there, but that table would just be a translate of one of the tables that we've already drawn. So instead of saying when the trajectory leaves the lower edge that it goes into a new table, we just say it goes to this parallel edge above it, and then continues in that gadget. So what that means is that the evolution of this billiard trajectory can be described just using this associated figure, which I call the Swiss cross. And now the edges represent no obstruction to the billiard flow. You just glue them together, the corresponding edges together by translation, and you get a closed surface. On this surface, you have a Euclidean metric, and the billiard flow is nothing more than the geodesic flow for that flat metric on a surface of genus 2. Now, you might wonder, how can there be a flat metric on a surface of genus 2? That's a good thing to ask. So it turns out that this metric has singularities. And in fact, you get more structure than just a metric. You can take the one form, dz, on the plane. Since dz is invariant under translation, it also glues up to give you a holomorphic 1 form on this quotient Riemann surface. And this holomorphic 1 form has to have some zeros. But dz doesn't have any zeros in the plane. So where are the zeros coming from? Well, they're coming from the inner corners of the Swiss cross. That is, it turns out that all 4 of those green inner corners glue up to give a single point on the surface of genus 2. And the total angle of the Euclidean metric around that point is much more than it should be. Namely, it's 6 pi. And what that means is that you get a holomorphic 1 form on the surface of genus 2, which has a double 0 at that unique point. And it has no other zeros, because a holomorphic 1 form has 2g minus 2 zeros on the surface of genus G. OK, so this is a way to start with a billiard table and from it get a Riemann surface plus a 1 form. So we go from the billiard picture into this algebraic geometry picture here. Now what? Well, it turns out that in the special case where that 1 form generates a totally geodesic algebraic curve in moduli space, that is, when its stabilizer in SL2R is a lattice, when it generates one of these so-called Teichmuller curves, which are arising as the closure of a complex geodesic, that this lattice, this polygon, I should say, has a very special property. Namely, in that case, the billiards in P is optimal. Every trajectory is either periodic or uniformly distributed. This is a theorem of Veitch and Mazur that relates this picture in moduli space to a naive picture about the dynamics of this billiard. Well, as you can see here, a tremendous number of people have worked on this field, and I don't have any time to summarize their results. But if I had to say in one word what goes on here, that word would be renormalization. Everything is about taking the geodesic flow and accelerating it so that you can see more clearly what happens over a long period of time. And that acceleration process is called, in dynamics, renormalization. It involves taking very carefully chosen first return maps. OK, so now let's ask our billiard theorists for some examples of these lattice polygons, because they will give us these curves in moduli space. So here are the lattice billiard tables that were known in the 20th century. There's the square. And in this case, the associated lattice is SL2Z. And this, of course, corresponds to the familiar fact that a geodesic on a flat torus is either periodic or it's uniformly distributed. If it has irrational slope, then it goes everywhere. Now, there's a variation on that billiard table, which is, for example, the following billiard table is also dynamically optimal. And why is it dynamically optimal? Well, because it's built out of squares. And it turns out that that easily implies the associated stabilizer is a subgroup of finite index in SL2Z. So this is another example, but it's not a very interesting new example. It's just a variation on the preceding example. So this kind of example, the square we say is a primitive example. And then these variations on it, which just give other groups of finite index, are imprimitive. So our real interest is in these primitive examples. And here's what was extremely striking was when Veitch proved that the regular polygons are also lattice billiard tables. And his proof shows that, in fact, the corresponding lattice is the 2n infinity triangle group in SL2R. And then in the 20th century, there were various sporadic triangles known whose groups were also triangle groups and which were also billiard tables. I may say a word about them later. OK, but as someone stuck in genus 2, let me go back to that genus and ask how many examples have the 20th century billiard theorists now given me? Well, it turns out that only the regular pentagon, octagon, and decagon give genus 2 examples. If you take these regular n-gons and let n go to infinity, the genus also goes to infinity. So this raises immediately an important question apropos our classification theorem. Are there infinitely many primitive Teichmuller curves in the moduli space M2? Are there only these 3 examples coming from regular polygons? Or are there infinitely many other examples waiting to be discovered? OK, so this is the problem I first became attracted to in this area. And the means of attack is the following. We ask ourselves, if there are going to be these special curves in moduli space, where are they going to lie? What's going to be special about these Riemann surfaces that have these big stabilizers under the action of SL2R? And what, by the way, is also going to be special about their one forms? Now, the first thing you might guess is that the Riemann surface has to have some special symmetry. That, unfortunately, turns out to be wrong. What happens is you get this group in SL2R. The elements of SL2R acting on the complex plane are not holomorphic maps. And in terms of the symmetries of this surface, what you find is your Riemann surface has a lot of symmetries, but these symmetries are not holomorphic. The derivatives of these symmetries with respect to the given charts are 2x2 real matrices that are only very rarely going to be give you complex analytic functions. However, it's well known that there's a way to take your Riemann surface and turn it into a group. Namely, every Riemann surface of genus G is contained in a complex torus CG modulo a lattice, which is really just the lattice of periods of a basis for the space of one forms. And this lattice, called the Jacobian of the surface, is isomorphic to just a big torus, S1 to the 2G. And it turns out that this object has a much richer group of symmetries in general than this object does, because as a torus, it admits not just automorphisms, but endomorphisms. And so you can ask, what is the endomorphism ring of the corresponding Jacobian? And it turns out that the surfaces, the curves we're looking for have to have special endomorphism rings. And they have to, technically what one says is that the Jacobian has to admit real multiplication by OD, where OD is the real quadratic ring of discriminant D. And these kinds of special Jacobians or special abelian surfaces have been very well studied. They sweep out what's called a Hilbert modular surface inside of moduli space. And as a corollary, we don't have to look for the Teichmuller curve in this three-dimensional moduli space, oops, but instead inside of this much smaller two-dimensional hypersurface. OK, let me, yeah.
Can all possible D's appear?
Yes. Good question. We'll see. So let me just tell you the idea of the proof. The idea of the proof is based on something you teach in linear algebra. If you have a 2x2 matrix of determinant, well, actually, I guess it's, yeah, of determinant 1, then A plus A inverse is just the trace of A times the identity. And so what that means is you have these maps of the Riemann surface to itself. If you could somehow add this map to its inverse, you would get a holomorphic map. But you can't add the map to its inverse because the Riemann surface is not a group. However, if you pass to the Jacobian, then it does make sense to add these endomorphisms. And as a result, this transformation A plus A inverse determines an endomorphism of the Jacobian. And what that means is that the trace of that matrix times the identity generates some field, and that field acts on the Jacobian of X. It sits inside the endomorphism ring of the Jacobian, say, tensored with Q. OK, so this simple idea that the trace, what this really shows is that if you have a lattice in SL x omega, then the trace field of that lattice will be visible inside the endomorphism ring of the associated Jacobian. OK, so anyway, there's going to be some associated real quadratic field to each of these Teichmuller curves. And that's not too surprising. I mean, the fifth roots of unity are associated to the golden mean. The real part of a fifth root of unity generates the same field as the golden mean does. So in the background of each of these examples, there's some sort of quadratic field in the case of genus 2. And now all we have to do is somehow cut our search down by one more dimension. So we need an additional condition to define a one-dimensional subvariety of moduli space. And this is hinted at by the example we've seen. Namely, in the example we saw, the holomorphic one form had a double zero. This is not generic. A typical one form of genus 2 has two simple zeros. So let's ask that not only does the Jacobian have special symmetries, but the eigenforms attached to those symmetries are one forms with double zeros instead of two simple zeros. That defines a sublocus of the Hilbert modular surface, which is one-dimensional. And then it's almost trivial to prove that that sublocus is a finite union of Teichmuller curves. It's by definition an algebraic subvariety. And anyway, it's straightforward to check that it's totally geodesic, or that the corresponding one forms are invariant under the action of SL2R. So I like this theorem because of the fact that the proof of the theorem is a definition. As soon as you write down this definition, the proof becomes trivial. It's just a synthetic construction. And as a corollary, we get lots of new Teichmuller curves. We can show, for example, that the L-shaped table with ratios, with side ratios that I've described here, short sides of length 1 and long sides of length gamma. Gamma would be the golden mean when d is equal to 5. All of these L-shaped tables, as d varies, are lattice polygons. They all have this good dynamical behavior. And as a consequence, there are infinitely many primitive Teichmuller curves in genus 2. We only saw a few, but we can vary d and get infinitely many different fields, and therefore infinitely many different curves. OK, now a couple of puzzles arise. What happened to the regular pentagon? Now I have all these L-shaped tables. Well, after about a week of messing around with elementary geometry, you might discover the following construction. So if you take the golden table, that is the table where the long sides have length the golden mean and the short sides have length 1, and you trim off its two corners, put them on the bottom, and then stretch the whole object, you'll get a union of two pentagons, regular pentagons. And what that means is that the Teichmuller curve generated by this guy is the same as the Teichmuller curve generated by the other guy. They have the same SL2R orbit. So this operation is a sort of scissors congruence. And because this scissors congruence exists, once we've given the golden table, we have actually given the same example as the pentagonal table. So this brings us back to this issue of classification I mentioned. How can we tell when we've given the same Teichmuller curve twice? The pentagon and the golden table are different ways of talking about the same curve in moduli space. So here is perhaps the most embarrassing theorem in this subject so far. It's very easily stated. This curve is irreducible, except in some special case where there's a spin invariant which allows you to see it has two components. And what that means is once you've computed the discriminant, you know what curve you're talking about. The discriminant is essentially a complete invariant. Now what's strange about this theorem is that although the statement is very simple and could be said between the main course and dessert to an algebraic geometer, I don't have any idea how to prove it nicely. The current existing proof involves the consideration of thousands of cases and using some approximate regularity in the behavior of small primes to examine the infinitely many cases that remain. And it's done by enumerating the cusps of this curve WD, which is a complicated but doable combinatorial problem, and then finding elementary moves that prove that two cusps belong to the same component. That reduces the proof of irreducibility to the proof of connectedness of some combinatorially described graph. And then you just try as hard as you can, and eventually you prove that these graphs are connected. So it's not satisfactory, and it would be really nice to have a deep explanation of why these curves are irreducible. By the way, there's a lot of beautiful geometry lurking here I don't have time to go into, but Matt Bainbridge in his thesis computed the Euler characteristic of these curves. And he showed that they're proportional to the Euler characteristic of the ambient Hilbert modular surface. And as a consequence, these Euler characteristics form the coefficients of a certain modular form. And this kind of observation shows that these Weierstrass curves fit very nicely into the theory, analogous theories like the Euler characteristic of moduli space, the Euler characteristic of the moduli space of abelian varieties. All of these gadgets have the property that their Euler characteristics are related to, say, special values of the zeta function or other gadgets associated to modular forms. And this shows somewhat surprisingly that the Weierstrass curve fits into this picture. I'll just say for the experts, the reason this is surprising is that this Weierstrass curve is not a Shimura variety. It's a nice curve sitting on this Hilbert modular surface. There's some obvious beautiful curves on a Hilbert modular surface, these Shimura curves. This is not one of them. And so it's a bit surprising that it has all these good properties. OK, but this was just the warm-up. A typical form in genus 2 has 2 zeros, not 1. 2 simple zeros rather than 1 double zero. And by the way, what happened to the regular decagon? So here's something we don't usually teach in topology courses. Construct a surface by taking the regular tangon and identifying opposite sides. So if you do that, what is the genus of the resulting surface? It's 2. But we usually don't teach that because it's inefficient. You can also take an octagon and identify opposite sides and get a surface of genus 2. So why do a tengon? And in fact, the inefficiency of the tengon is evident in the following fact. The vertices of the tengon fall into 2 classes under this identification of opposite edges, these blue and red ones in this picture. And as a consequence, if you construct the corresponding holomorphic 1 form, it has 2 simple zeros instead of a unique double zero. So this is another gift from Veitch. It's an example of a 1 form with 2 distinct zeros. It's much more generic type that also generates a Teichmuller curve that also gives a billiard table with optimal dynamics. Several years ago, I sat down to write a program, a computer program that would investigate this tropical forest of holomorphic 1 forms with 2 distinct zeros and look for Teichmuller curves there. And since we'd found so many examples with double zeros, I was confident that there would be many more where we had the more generic condition of 2 simple zeros. And so I spent a month writing this program, and then I cranked it up and started running it. And the only thing it found was the regular decagon. And so then I started to wonder if perhaps instead of standing at the edge of a tropical forest, that I was standing in an oasis in a vast desert with maybe 1 palm tree out there. And in fact, that turned out to be the case. So the main result here is that there is only 1 other primitive Teichmuller curve in genus 2, and it is the one you've just seen coming from the regular decagon. It's much harder to find examples with 2 simple zeros than a double zero. And the reason for this is explained by the following beautiful result of Martin Müller. So here I've drawn a picture of a curve of genus 2 in the projective plane, and I've chosen 2 points on it. These 2 points I've chosen are actually the zeros of a holomorphic 1 form. And what Müller showed is that if you're going to have 2 distinct zeros, and this form is going to generate one of these good curves, then the difference of those zeros has to be torsion in the Jacobian of x, in this associated commutative group. And that's a very stringent condition on this divisor, p minus q. For example, geometrically in this picture, well, what does that mean first? In terms of Riemann surfaces, it means that there's some meromorphic function on the curve that has a pole of high order at p and a 0 of high order at q, and no other zeros or poles. And in the case I've drawn here, there's a meromorphic function with a pole of order 5 at p and a 0 of order 5 at q. And that corresponds to the fact that this curve can be osculated to extremely high order at p by an algebraic curve of low degree. That's what you see there, that transverse curve, which almost matches the algebraic curve here. OK, so with this great new insight of Müller, who really brought a lot of new techniques to the field, brought sort of the whole theory of variation of Hodge structure into the discussion, we have a potential handle on further classifying these examples. And the next step is to take this curve of genus 2 and degenerate it to a rational curve so that we can understand it even better. So if you have a curve of genus 2 with these two handles on it, you can pick two curves like this and pinch them to points. And when you do that, what's left over is a stable algebraic curve of genus 0. That is a rational curve. And in terms of this algebraic geometry picture, it means that the curve in the plane acquires these two nodal singularities. And when it does, you can put the equation for the curve into this nice form with sines and cosines. And now we leverage the two pieces of information we have, namely that the difference between the zeros was torsion. That's from Miller's theorem. That implies these angles that appeared in the previous equation are rational. And then the fact that the Jacobian had real multiplication by some quadratic field means that the ratio of the sines of these angles must be a quadratic number. Well, that's very unlikely. It turns out there's only 15 examples of rational angles whose ratios are quadratic numbers. And among those, one gives you the golden mean as the ratio, and this gives rise to the regular decagon. And the remaining 14 don't work. And so that's the proof of the theorem. So from this all, we find that there really wasn't much left to discover beyond what we've already found. And consequently, we can classify all the dynamically optimal billiard tables in genus 2. There's either these simple variations coming from the square and the equilateral triangle. Then there are these L-shaped tables. And then there's the regular decagon. And those are all of the dynamically optimal examples in genus 2. OK, so what's left? Well, I want now to revisit, as I start to look towards higher genus, these exceptional triangles I mentioned. So on the left-hand column here, you see 3 special triangles that were discovered by Vorobets and by a computer search of Kenyon and Smiley, which were proved by hand to be dynamically optimal. Well, here's how we understand those examples now, due to an insight of Leininger. Associated to each of these examples is a Coxeter diagram. And from these Coxeter diagrams, you draw a configuration of simple closed curves on a surface. As you can see, the red and blue curves there meet in the same configuration as the nodes of the Coxeter graph. And now what you do is you take a Dane twist around the red curves and simultaneously around all at once. That's an element of the mapping class group of a surface of, say, genus 3 in the top example. And then you consider a second element, which is a Dane twist on the blue curves. And it turns out that these two elements together generate the stabilizer of a complex geodesic in Teichmuller space. And moreover, they generate a lattice. And consequently, that picture completely determines the corresponding Teichmuller curve. So you can go from this picture to this triangle by a fairly simple combinatorial procedure, which involves calculating the eigenvalue of a positive matrix. This procedure itself was invented by Thurston around the late 1970s. But the connection to these billiards was only lately discovered by Leininger, and gives a very efficient way to communicate what one of these Teichmuller curves is. If I tell you over the phone, take the E8 diagram and do this, you would be able to reconstruct this algebraic curve in the moduli space of curves of genus 2. And by the way, what happened to the other spherical diagrams, the AN and DN diagrams? Well, it turns out the same procedure works, but they just give the regular n-gons, which we already knew about. OK, but once this language is available, you can continue the discussion by trying to find new examples. And it turns out that our L-shaped tables can be described by just a small variation of this language, in which we allow weights on the simple closed curves. And what that means is you do a power of a Dane twist rather than the Dane twist itself. And in terms of those weights, our L-shaped tables just correspond to the A4 diagram, just to 4 vertices sitting in a straight line. The second thing one can leverage is the fact that every surface of genus 2 has a symmetry. It's a hyperelliptic curve. Well, you can also construct curves of genus 3 and genus 4 that have special symmetries of that ilk. And when you do that, it allows you to replace their high-dimensional Jacobian with the lower-dimensional prim variety of odd forms. And then you can make the corresponding complex multiplication, real multiplication discussion, and it all turns out to work. So these pictures here can be, again, sent over the phone to prove that there are also infinitely many primitive Teichmuller curves in genus 2, 3, and 4. And this kind of brings us up to the boundary of present knowledge. And it's not at all clear whether or not we just have a sporadic set of ad hoc constructions and we are awaiting to discover the tropical forest of higher genus, or whether, in fact, we've reached the limit of what can actually be done. And it's very interesting and complicated to try to analyze what happens in genus 5 or even just in hyperelliptic curves of genus 5. And there's a lot of ongoing research on this topic. So let me conclude by retreating further. So I already retreated from Kleinian groups to and rational maps to this theory of billiards, which is much more linear. Then I retreated from all genera to genus 2. I took a peek at higher genera. It looked too confusing. Let me retreat back to genus 1. So the theory of billiards in Riemann surfaces of genus 1 is really just the theory of the slope of the billiard trajectory. All the billiard tables are equivalent dynamically. You might as well take them to be the square. And the issue of the dynamics of a given billiard trajectory has to do with the issue of the Diophantine nature of the slope, how well it's approximated by rational numbers. So here's a result, a new result from a year ago or so about Diophantine approximation. And I'll later reinterpret this in terms of billiards. This result says every real quadratic field contains infinitely many uniformly bounded periodic continued fractions. Now, what does that mean? Well, here, let me just give you an example. We all know the field Q adjoin root 5 contains the golden mean. The golden mean has the continued fraction expansion 1 over 1 plus 1 over 1 plus blah, blah, blah. Well, it turns out it also contains these periodic continued fractions, 1 over 4 plus 2 over 3 plus 1 over, etc. So you just keep repeating those numbers. It's well known that a periodic continued fraction gives you a quadratic number. What's remarkable here is that we don't use any large numbers. All of the numbers remain less than or equal to 4, and they all lie in this fixed field, Q adjoin root 5. When I discovered this, I realized that either this was a new result or it was an ancient result due to Lagrange or Gauss or perhaps Euclid. So I consulted with the experts all over the world by email and determined that if it was an ancient result, then it had been forgotten. But it hadn't quite been forgotten by everybody. It was remembered by Google. So Ashke Venkatesh thought of the right words to type into Google. And as a result, he found this 1978 paper in the Journal of the Australian Math Society by Wilson and Woods, which in fact contains exactly this example. So anyway, this is the theorem that there are lots of these bounded continued fractions in a fixed quadratic field. What this means geometrically is that you can find very long geodesics on the modular surface, that is H mod SL2Z, one of which I've drawn lifted to the upper half plane here, which stay away from the cusp. That is, they avoid some big horrorballs here. So this is an extremely long geodesic, and yet it's staying a uniform distance away from the cusp, and it's defined over a fixed quadratic field. And in terms of billiards, what this means is that if you take the golden rectangle and you say, I only want to understand the dynamics at rational slopes, then there are infinitely many different rational slopes that are optimally distributed. Now, what do you mean optimally distributed? How can a rational slope be optimally distributed? Well, it means that it becomes uniformly distributed as more or less as quickly as it can. So just let me show you this by a picture. This is an example of a resonance slope. And you see it's favoring some parts of the table over others, whereas this is an example of an optimal slope. It's very well spread out. And there are infinitely many such slopes, and as you can see, they have something to do with Fibonacci numbers and so on. And all of this can be done for a general real quadratic field. OK, so let me conclude by posing an open problem in the theory of billiards in genus 1. That is, in the classical theory of continued fractions. So I've shown you, by exhibiting a certain pattern of numbers involving 1, 2, 3, and 4, that there are infinitely many continued fractions in the field Q adjoin root 5 that have all the AIs less than or equal to 4. Now, it seems that much more should be true. What should be true is that if you look for the number of such continued fractions of length p, that is with period p, that the number of examples should grow exponentially as the period goes to infinity. And there's plenty of open questions here. For example, I know only a couple of examples that lie in Q adjoin root 5 where all of the entries in the continued fraction are just 1 or 2. But nevertheless, there's a reason to believe that they should grow exponentially fast. So let me say why they should grow exponentially fast. You see, in the dynamics of the geodesic flow on the modular surface, there's a lot of hyperbolicity. This hyperbolicity forces the rapid growth of periodic points. There are certainly exponentially many geodesics of length less than or equal to L that sit in a compact part of the modular surface. That means that's tantamount to just saying there are infinitely many periodic continued fractions with the AIs just equal to 1, 2, 3, or 4, and with very large period. After all, the number of such is roughly 4 to the p. And now the question is, if you take that dynamically obvious chaos and you filter it by a particular field, say Q adjoin root 5, is the trace of it within that field exhibit the same property of exponential growth? And if this were to obtain, which I hope it does, I would call the phenomena arithmetic chaos. So I'll conclude with that as the conjecture that there should be this exponential growth. And this conjecture resonates with many existing elementary conjectures in number theory. And it also resonates with a deeper kind of intersection between chaos and arithmetic, quantum arithmetic chaos, or arithmetic quantum chaos, which we may hear more about this afternoon. Thank you.
You said the family of tight unit curves, you consider the tight unit curves sitting inside Hilbert modular surfaces. And you said they were not Shimura curves. So can you directly see that they don't contain more than a finite number of CM points?
No. Excellent question. So we know very little about the CM points on these curves. And in fact, there's an ongoing investigation right now of just when they admit CM by the field Q adjoin root D and I, which just means when does the curve have a symmetry of order 4. But we know nothing about the general intersection with Shimura curves. And of course, the conjectures would be that there are only finitely many, because otherwise you should be on a special curve. So as you say, the Andre Oort conjecture is relevant here, but I don't think we get any insight into it, even though we're learning a lot about these curves.
Can you give a specific form on which, so you say these curves lie inside of the Hilbert modular space, right?
Yes.
So can you give a Hilbert modular form on whose zeros are that?
Yeah, so this is exactly what Matt Bainbridge did to compute the Euler characteristic. So it's a little bit like our knowledge. We know very well what the pole of the Weierstrass P function is, but it's hard to say what its zeros are for a given lattice. Well, in the same way, you can find a form on one of these Hilbert modular surfaces, or a cross-section of a suitable line bundle, whose divisor is comprised of a finite union of Shimura curves, some of which are supported at infinity. So you have to compactify the variety. Say that's the poles of the form. And the zeros of the form are this WD, this curve of interest to us. And that form is defined by integrating the given one form between the two zeros. And that vanishes when the two zeros come together and allows us to make this analysis.